Uh, Thank you all. Thank you for giving me the opportunity to present at this beautiful conference. I'm really enjoying it. So I'd like to present my work with Professor Wes Campbell in UCLA and Ken, just hosting me, on erasure conversion on trapped ion qubits. We have several talks on erasure conversion in this conference. We had heard several times on Tuesday, and the next talk is about it as well. I hope you all use this as an opportunity to see how this erasure conversion idea gets applied to all these various quantum platforms, and really what are the challenges for each platform, which are all different, which is fun, you know, and at the implementation level. So yeah, with that, I'll begin. So erasures are errors with known location. So in the classical case, we think of bit flips, 0 being 1, 1 being 0. But we also think of erasures, where 0 and 1 both become some eraser mark, let's say. And in the quantum case, we usually think of bit flips and phase flips. But we can also think of erasures, which is the qubit state becoming a known state, such as the maximally mixed state. And crucially, with the additional information that this happened at this qubit. And that's really good for error correction. The location information is important. So for the classical case, repetition code, the distance d code corrects d minus 1 over 2 bit flips. So to correct one error, you need distance 3 for bit flips. But if the errors were erasures, you only need distance 2, because you just look at the other qubit that's not erased. So yeah, this should give you an idea of why erasures are really good for error correction. And that's why people tried so hard to convert various physical noise in various platforms to erasures. So in the recent days, it all started from Professor Jeff Thompson and Shirley Puri group's work on Rydberg atoms. And I really have to say we're heavily motivated by this work. And there's also the work on superconducting qubits, which we'll hear in the next talk, I believe. So what's the common theme here? So it's the following. We just heard that leakage is so bad, but I'm going to propose that we have to design qubits so that physical noise causes leakage. However, you have to do that so that it's detectable whenever it happened. So yeah, for example, you can see that here, something happens, it goes outside the qubit subspace, and the same thing happens here as well. But only if it happens in a detectable way, you can use additional operations so that you can turn this leaked state to, let's say, the maximally mixed state in the qubit subspace, and that completes erasure conversion. So I really find this history of erasure conversion fascinating, so I'll give you a brief review. If you go back to history, the first proposal of detecting decay and using it for QEC actually was there in 2001 and 2005. But in the recent days, we all have these exciting platforms. So in January 2022, the proposal for Rydberg atoms came out. And then on August, we had the proposal for superconducting qubits, as we'll hear from the next talk. In October, I submitted this to arXiv. And then December, we had the proposal for cavity QED system, which we heard about on Tuesday. So yeah, things are moving very fast, and even faster when it comes to experimentally realizing it. So the first related experimental work dates back to 2008. A USDC from China demonstrated correcting one erasure on a 4-qubit code. However, I have to say it's not an erasure conversion, it's a injected erasure, because erasures are natural for photonic qubits. But then, May this year, the experimental realization for Rydberg atoms happened actually in 2 groups, led by Princeton and also in Caltech. Caltech focused more on quantum simulation, but yeah, it's also very cool. And on July, there was this experimental realization for dual-rail qubits, superconducting systems. So for transbonds, it happened in Amazon, and for cavity systems, cavity qubits, it happened in quantum circuits in Yale. So for the trapped ion experimentalists here, we have 2 months left. But I really hope this talk inspires trapped ion people to realize this idea, because I think it's really cool, and I'll make some remarks on that in the end of the slides. So we're going to talk about trapped ions. I'm sure all of you have seen this picture before. It's a very nice surface trap chip. You can trap 30-ish ions in a linear chain. And you can use lasers to individually address them and do single qubit gates and 2 qubit gates. You can also consider the quantum charge-coupled device architecture by Quantinuum, where you shuttle around ions so that each gate fidelity in each zone is really good. And we all know that Quantinuum has really nice quantum error correction experiments. And yeah, they use lasers to do gates too. So I'll briefly introduce the physics behind how to do these laser-based gates on trapped ion qubits. So for an example of a baryon qubit, we typically use the two hyperfine levels to encode a qubit in the ground fine structure manifold, the S-half. So these are the two qubit states. And unfortunately, they're split by 8 gigahertz-ish, which we cannot use lasers to directly make things resonant. So what we do is we use the 2-photon Raman transition so that we use these excited P states to virtually occupy them. And if the difference of the laser frequencies are resonant with the qubit frequency, then we can do all these single qubit and 2-qubit gates. And so yeah, of course we have the Rabi frequency for the gates, and the proportionality is given by mu e square over delta, where mu is the dipole transition matrix element between the S-half and the P states, and E is the electric field amplitude, and delta is the detuning from the P states. And yeah, so that's how the gates work. But what are the error sources here? So there's this fundamental error source, which is the spontaneous decay of these excited states. So these P states have a very short lifetime, about 6 nanoseconds. So they decay, and to various atomic levels. So if the decay happens to the qubit subspace, then it leads to bit flips or phase flips. And if the decay happens to other atomic levels, it becomes leakage. And we heard leakage is very bad. So yeah, there are previous works on how to handle these decay using QEC, this Brown and Brown work, font being Brown. Yeah, Natalie led this work when she was in our lab. And yeah, you can check these papers as well. Yeah, and what's the decay rate here, which is, of course, directly proportional to the gate error rate. The decay rate is proportional to mu e over delta everything squared. So the delta inverse versus delta square inverse, and that will become quite important later. And you can just multiply the gate time to get the error rates. Okay, so back to the key idea of erasure conversion. You need to design qubits so that physical noise causes leakage in a detectable way. So we know that there's leakage. How are we going to do that in a detectable way? The answer is using metastable qubits. So yeah, back to ground qubits, but if we zoom out, we actually see that there are also these other fine structure manifolds like D3 half and D5 half. And we can define these branching fractions, R1, R2, R3, a proportion of the decay rate to S half, D3 half, and D5 half. And usually, for all cases, R1 is the largest. So decay goes to the manifold where the qubit belongs. And that's quite challenging to detect. However, if we encode the qubit in the metastable D5 half manifold, then the gates work basically the same way, but then the largest proportion of the decay goes outside the manifold where the qubit is encoded. So now what you can do is you can use additional operations, which is resonant beams to the p-half state that do this optical pumping. So if you do that, you scatter a lot of photons, and you can detect them so that you know leakage to S-half happened whenever it did. And one important detail is these p-half states and d5 half states transitions forbidden. So even if we scatter a lot of photons, it will not destroy the other qubits in the same ion chain. So yeah, this is the big picture. Due to this idea, we can convert errors to erasures. And we can define this erasure conversion rate, which is the ratio of erasure rate to the total error rate. And from this picture, you can roughly estimate that as R1 plus R2. I say it could be higher because technically, in theory, you can pump other atomic levels in the D5F and pump it out as well, but you really don't want to mess with the data, the qubit encoded, so I'm going to take a rather conservative estimate here. And you might be also worried metastable qubits have a shorter lifetime. However, first of all, it's pretty long for our interest. And second, even if it happens, it decays to the S-half manifold, so it's, again, erasures, which is a favorable kind. So most of the work was actually a lot of atomic physics calculations, which I really enjoyed. And here we really have to consider the hyperfine and Zeeman splitting because qubit is encoded in those levels. So you have to calculate the Rabi rate, this coefficient. And there's an interesting relation with the branching fraction to the detuning that you have to consider. And from atomic physics, you can calculate all these rates that lead to phase flips, bit flips, undetected leakage, and erasures. And from that, you can come up with a more precise formula for the erasure conversion rate. So we calculate that for two species of ions, barium and calcium. And the erasure conversion rate turns out to be 79% and 95%. An interesting point is this is actually a little larger than R1 plus R2, mainly because of this detuning dependence relation. Okay, so yeah, we can convert a lot of things to erasures. That's very nice. Oh yeah, and these are the actual error rate plots. Here, an important thing is I'm using the detuning to tune as a knob to tune the error rates, and that's because of the proportionality, the error rate is inversely proportional to the detuning, and does not explicitly depend on, for example, the gate time. And yeah, there's a busy plot, but the main takeaway is that basically for ground qubits, most of them are undetected leakage, and for metastable qubits, most of them are erasures. So now the time for error correction. We're gonna apply the error model that I just described to error correction simulations. And for an example, we're gonna use the surface code, our favorite code, or not so much, I don't know. So yeah, we have the third CNOT gate here that's hypothetically leaked out. And then you reset to the, whenever you detect it, you reset to the metastable manifold, and then apply a I or X gate probabilistically to make it into a maximally mixed state. I want to emphasize that erasure conversion is not limited to surface code. The location information is always valuable. It applies to all QEC codes. I choose surface code because it's really relatively easier to get the threshold than simulations. And for surface code, it's really easy to visualize why location information is so valuable. I borrowed this picture from the pi matching paper. And yeah, what happens is these errors in the red edges occur, but you only have, usually, you only have these syndrome, the blue stars available, and you have to do this matching from this complicated looking syndrome graph. But imagine you also have these red edges inside this graph and run algorithm on that, and you can imagine that will help the computer so much more. So yeah, knowing the location of errors should improve the threshold. And by the way, I got several emails about how I simulated this, and the answer is STIM. STIM is amazing. I would really like to thank Craig Gidney for developing this tool. He recently added this heralded erase command, and we also have some tips for people in the quantum stack exchange. So if you're interested in simulating these, please use STIM. It's very nice. Yeah, so these are our favorite threshold plots. And now we're comparing the ground qubit and metastable qubits performances for barium and calcium, which has these erasure conversion rates. And yeah, it's pretty obvious that metastable qubits has significant improvement in the threshold. And if you compare vertically, the decrease in logical error rate is quite dramatic. So yeah, metastable qubits and erasure conversion improve the threshold. The original Rydberg-Adam paper also suggested to look at the slope, which is how steeply your logical error rate decreases as you decrease the physical error rate. And that's what we call the error distance. So if we only have bit flips and phase flips, this slope's supposed to be d plus 1/2. And if we only have erasures, it's supposed to be d. And for barium and calcium, they're somewhere in between. So additional to the threshold advantage, we also have this slope advantage, which is very nice. Okay, so if this was the end of the story, I would immediately go tell everyone, please use metastable qubits. But as everything in life is, there are trade-offs. And so what are the trade-offs? Well, we have to first go back to why we had this erasure conversion in the first place. And that was because we had this R1 branching fraction much larger than R3. And why was that? That was because your dipole transition matrix element was much stronger to the S state than the D state. So that's the mu here. But you also notice that the Rabi frequency is also proportional to mu squared. And that means, by the same reason erasure conversion worked, your ground qubit's Rabi frequency is stronger for fixed detuning. So, and that's somewhat advantageous for ground qubits because stronger omega means a shorter gate time. So that motivated us to make comparisons under fixed Rabi frequency so that you can fix the pulse time and fix the error rate due to other sources of errors like technical noise, the experimental noise whose effects build up with gate time. So these are the three cases we're considering. You already saw the first case. And for case 2 and 3, we're fixing the Rabi frequency. And we have an additional choice of fixing either the electric field strength or the detuning. And if we're fixing the detuning, it means we're using a larger laser power for metastable qubits. And that sounds a little unfair, but I'm going to argue it's actually reflective of the experimental constraints because first, metastable qubits use lasers with longer wavelength, just because it's closer to the P states. And we're not really limited by the laser power like directly from the, the laser itself, but we are rather limited by lasers burning mirrors. Happens in our lab all the time. So this is what happens when you have too strong laser, too high short wavelength laser on the mirrors. So we can't afford this. And since metastable qubits use lasers with longer wavelength, we believe that this EM larger than EG is a realistic regime to consider. Okay, with that, let's look at case 2 and case 3. So how you read this plot is the vertically aligned ground qubit physical error rate and metastable qubit error rate corresponds to this case. So yeah, if you look at case 2, ground qubits, dashed lines, are below metastable lines, which means that ground qubits win. All the advantage from erasure conversion is gone. However, if you look at case 3, larger power for metastable qubits, well, for barium, the threshold improvement shrinks quite a lot, but actually the slope advantage still holds. So if you go to lower error rates, we still have quite an advantage. And for calcium, because it had a larger erasure conversion rate, the advantage remains by quite a lot. So metastable qubits win in this case, with a caveat that it might require 2 to 4 times larger electric field strength. And probably the reality is somewhere in between. It depends on the material you're using. So yeah, I'll leave that to the experimentalists. So summary and remark here. So erasure conversion on metastable qubits improved the QEC threshold. And metastable qubits should outperform ground qubits when larger laser power is allowed, which we find to be a reasonable assumption. By the way, here, a remark is that we're simulating undetected leakage as we treat them as depolarizing error. However, we all know it's not. So if we simulate this more rigorously, then we believe that advantage of metastable qubits should be actually much larger because, for ground qubits, most of it is undetected leakage, but for metastable qubits, most of them are erasures. So now I'll briefly discuss the prospects for experimental realization. So I want to say metastable qubits have been already promising before this work. In particular, this very nice work proposed that by using a mixed chain of metastable qubits and ground qubits, you can do mid-circuit cooling and readout, which can replace the mixed species ion chain. And in 2022, a group from Tsinghua University in China experimentally showed that you can convert ground qubit state to metastable qubit state and vice versa. And this process was pretty good fidelity, and this was done in like less than a microsecond, so it was pretty fast. So we know we can do this. And however, one criticism you might have for this work is the spontaneous decay is not usually the major source of error in state-of-art gates. Now I'd like to say that that's because we always considered this large detuning limit. So we use this large detuning to decrease the spontaneous decay rate, because that was the bad undetected leakage. And that led to longer gate time, basically. The rabbit frequency was smaller. However, now we know that for metastable qubits, the detuning should be, the decay is actually not that bad of an error type. So we can consider using smaller detuning, and that will increase the spontaneous decay rate, which is fine, and decrease the gate time. So decrease all these errors due to experimental noise building up. So yeah, decreasing detuning here seems to be converting technical experimental noise to erasures. And this seems to be a different kind of erasure conversion, so I think it's quite exciting. And the logical error rate is what really matters. So yeah, I hope this is experimentally realized soon. And that's not the end of the story. There's also, you can convert other sources of errors in the same trapped ion platform to erasures. For example, our co-author, Wesley Campbell, considered detecting the over-rotation error whenever it happens by using the metastable qubit. So he didn't use the language of quantum error correction, but it's basically erasure conversion. The idea is you use these auxiliary levels so that over-rotation leads to a residual population, and you can pump it out. So that's great. And the state-of-art gates all have these errors due to motional dephasing and heating, which are actually the leading source of errors. I've been fighting them for a while, and the experimentalists in our lab actually saw some improvement in the gate fidelity by pulse optimization. Yeah, but we heard from Professor Shirdi-Puri's talk that fidelity is not the only measure we need to consider. So if we change the error type for these sources of errors as well, that would be very exciting. Yeah, with that, I would like to wrap up. I would like to thank my co-authors, Professor Wes Campbell and Kim Brown, for this awesome collaboration. And we had a large group of people from Duke. We had these amazing posters, not only hardware stuff, but also, yeah, error correction theory stuffs. And yeah, if you recall these titles as interesting, please talk to the authors for the remaining conference. Yeah, thank you for listening.
Questions for Mingyu? Yes.
Hey, Mingyu, thanks for the nice talk. So I have two questions. The first one is very specific. What limits the erasure conversion rate for different atoms?
Yeah, so we calculated for the barium and calcium ion, which was 79 and 95% respectively. If you just need a rough guess, you just look at the branching fractions, look up the papers that measured those. They're very nice measurement papers for all various species. So yeah.
So do you have any idea like what kind of atoms have the highest erasure conversion rate?
Yeah, calcium has the highest for the ions I considered, yes.
Yeah, I see. So, and my second question is a little bit more general. So, so we know that when you do the erasure conversion, you actually gain some information from your loisy qubit, and actually from the viewpoint of entropy, you're taking some of the you're moving out some entropy from your loisy qubit, right? So, how do you see this kind of erasure conversion process in this kind of viewpoint?
Yeah, that's a very interesting question, and I think it's related to Professor Shirdi-Puri's talk, where she, I think, considered all these code capacity for different types of errors, and yeah, that's all related to entropy measures, so I guess that could answer your question. Yeah.
Yeah, thanks.
Thanks for a very nice talk. So in classical coding theory, erasure codes are usually used with non-binary codes. So do you expect that something similar may happen here? So for example, maybe you will have more advantage if you use your techniques with qubit codes instead of qubit codes.
Yeah, that's a very, very nice question. And yeah, I find it also very interesting. Like metastable manifold has a more atomic level, so they're naturally more suited for qubits. So yeah, that'd be very interesting to explore. Yeah, and it should be that some codes are well suited for erasures than other codes. Surface code might be the optimal choice for this comparison. However, we can't have perfect erasures. So I guess there's a space of codes that we should look at, but yeah, there's a lot of optimization to do in that respect. Yeah.
Thank you.
Very nice talk. Can you comment on your choice to look at barium and calcium? Was it just laser power you're considering, or was there some deep atomic physics of why you chose to look at those two?
The primary reason was the type that I could look up the branching fractions in the literature. That was the main reason. Strontium was also available. I think the lifetime was shorter or something, so I didn't choose it. And for ytterbium, I wanted to choose ytterbium, but for the ytterbium, D5 states have a shorter lifetime, so you usually look at the F7/2 metastable states, but then you don't use the P states for the two-photon Raman transitions, so you use the exotic states that are not, the branching fractions are not measured yet, so unfortunately, yeah, but yeah, ytterbium F7 is also very, very promising because they have like almost infinite lifetime, and yeah, yeah.
So, and you said calcium had the best rate here. Do you expect a different ion to have an even better rate if you were to be able to sweep through the periodic table?
Yeah, I don't see any reason why calcium should be the best. Yeah, for ytterbium F7 I guess it's more complicated because you're using these exotic states, but the branching fraction itself could be larger. Yeah, I guess we all need to measure, the experimentalists can explore all these other ions for that, yeah.
Thank you.
All right, let's thank Mingyu again.